All right, today we're going to tackle something that seems, well, almost impossible: the mathematics of the unpredictable. We're going to go on a little journey to see how we can actually model random things that happen over time using a really powerful tool that, you'll see, pops up in some pretty unexpected places.
So, what do these things really have in common? I know, it sounds like the beginning of a bad joke, but believe it or not, all of these seemingly random parts of our lives can be understood and even predicted using the exact same mathematical framework. It's pretty wild. So, let's get into it.
Okay, before we can get to the really cool stuff, we've got to start with the basics, the very first building block. See, before we can model how things change, we first need a way to just, well, count random things as they pop up. So let's put ourselves in the shoes of an insurance company. You know claims are going to come in. That's a given. But you have no idea when or how many. So how on earth do you prepare for that? What's the model? Well, this is their secret weapon, the Poisson process. It's basically the go-to model for counting random stuff. Think car crashes, calls to a customer service line, you name it. And the key thing to get here is it's not about predicting the exact moment something will happen. No way. It's all about understanding the average rate at which these things happen. And this timeline, it shows you exactly what that looks like in practice. Maybe the average is, say, 5 claims a day. But as you can see, they don't just show up every few hours like clockwork. They're totally random. You might get a bunch in the morning and then nothing for hours. That's the randomness the Poisson process is so good at capturing. Okay, now here's where it gets a little weird, but also super powerful. This whole thing has a feature called the memoryless property, and it's exactly what it sounds like. The process has zero memory of what just happened. The chance of a claim coming in this next hour, it's the same. It doesn't matter if a claim just happened 5 minutes ago or if it's been 5 days.
And this quote really drives that home, right? Because our intuition, our human brain screams at us, hey, it's been a week, a claim is due to happen. But the math, the model just says, nope, the past doesn't matter. The clock literally resets every single second.
So there you have it. That's building block number 1. The Poisson process lets us count random stuff. And the big takeaway is that memoryless property. The past has no say in the future. All right, we've got our first tool in the toolbox, counting things. But what if you care about more than just how many? What if you want to know how something's condition or state is changing? Well, now we're leveling up. And this slide lays it out perfectly. On one hand, the Poisson process is all about how many claims. But on the other hand, what we're moving to now, the Markov jump process, asks a totally different question. What state is it in? Are you healthy or sick? We're shifting from just counting to describing a state.
So here's the main event, the Markov jump process. It's a way to model a system, and that can be anything, a person, a machine, whatever, that randomly jumps between different states. The best analogy? It's like a board game. Your next move depends only on the square you're on right now. It doesn't matter how you got to that square. Sound familiar? Yep, that's that same memoryless idea coming back.
And these states can be literally anything. Remember that question from the beginning? This is the answer. You can model a person jumping from healthy to sick to dead. Or you can model their marital status, jumping from single to married, maybe to divorced. It's the same logic.
Okay, so we've got the states, and we know we can jump between them. But how? What are the rules of the game? We need some kind of speed limit that tells us how fast or slow these jumps happen. And that's where transition rates come in. For every single possible jump, like from healthy to sick, there's a number, a rate, that basically acts as its speed. If the rate is high, jumps happen all the time. If it's low, they're super rare. Simple as that.
So you can imagine, for any model, you've got a whole bunch of these rates for all the possible jumps. And the cool thing is, you can gather them all up and put them into one neat, tidy rule book that explains the whole system. And this is what that rulebook looks like. It's called the generator matrix. Now, don't let it scare you. It's actually pretty simple. It's just a grid. The rows are where you're starting from, say, healthy. The columns are where you could go, like sick. And the number in the box is just the speed limit for that specific jump. Oh, and check out the dead row. See how it's all zeros? That makes total sense, right? Once you're there, you're not going anywhere. It's an absorbing state. Okay, so we have our rulebook. Now we need a way to actually use it. And that's where this little equation comes in. Yeah, I know, it looks like some serious math, but I promise, the idea behind it is actually super straightforward and really powerful. Here's the best way to think about it. The matrix, that's our rulebook. This equation? It's the engine. You feed the rulebook into the engine, turn the key, and it just starts calculating the probability of being in any state at any time in the future. That's the magic trick right there. It takes a static set of rules and turns it into a predictive engine. This all sounds great on a whiteboard, but where do these numbers, these speed limits in our rulebook actually come from? How do we connect all this theory to reality? I mean, that's the million-dollar question, right? A model is just a fantasy without real data. So how do you actually figure out the number for something like a healthy person getting sick? Well, it's actually a pretty logical three-step process. Step 1, you just watch. You follow a group of people over time. Step 2, you write stuff down. You record every single jump. Who went from single to married? Who went from healthy to sick? And step 3, you do some math. You use all those observations to figure out the rates that best explain what you saw. You're basically reverse engineering the rulebook from real life. And once you've done that, once you have a rulebook based on real data, man, the possibilities are just huge. We're talking pricing insurance policies, managing hospital beds, understanding why marriage rates are changing, even figuring out the value of complex financial contracts. It's this one tool that does so much. So that's the whole story in a nutshell. You watch the past to build a rulebook, and then you use that rulebook to power an engine that gives you a glimpse, a probabilistic map of the future. So now you get it. You have these two amazing tools in your mental toolkit, one for counting random events and one for modeling jumps between states. So the question for you is, what random process in your world are you looking at now and thinking, I could probably model that?